Perfect. Okay, so we're going to do this one here. What would you suggest we do first? Yeah, write some terms out. Exactly. That's always the best. You want to know, what the sequence kind of looks like. So x1 is 1, right? That's given. So to figure out x2, I might take n equal to 1. All right, so we get 1/4 of, what is that? 2 times 1 plus 3, that's 5. That would be 5 over 4. Okay, let's do another one. x3. Now I've got to take 2 times the previous term. So that would be 5 halves. Add 3 to that. So that would be 11 halves. And then divide by 4, because there's a 1/4. So that should be 11 eighths. Okay, 11 eighths. Great. Okay, let's do one more, just to see what's going on here. So for the next one, I have to take, I'm going to take 2 times this. That'd be 11/4. I'm going to add 3 to it, which is like 12/4. So 11/4 plus 12/4 would be 23/4, and then divide that by 4. That would be 23 over 16. Okay, does that make sense? You want to do another one, or you have an idea what you think? It'd be nice to get an idea what you think it's converging to. I don't know if we see it yet or not. Just do one more. Why not? I can do a little more math. So let's take 23/16. Let's double it. That would be 23/8 plus 3, which is the same as 24/8. So 23 plus 20, that's 47/8. Divide that by 4, and we get 47 over 32, right? Okay. That seem all right? So does anybody have a notion what that's looking like it's converging to? These fractions? Does it look familiar at all?
1/2. Oh,
1/2 would be less than 1. 3 halves is a very, very good guess here. If the numerator was 1 larger here, this would be 6 over 4. That's 3 halves. If this numerator was 1 larger, 12 over 8 would have been 3 halves. If this numerator had been 1 larger, 24 over 16 would have been 3 halves. Right? It's almost 3 halves. So I would claim, the claim that I would make is that xn is converging to 3 halves. Okay, it seems reasonable. By the way, the other way to figure out what it's converging to, if you didn't see a pattern with the numbers, is to say, well, we're going to prove that this does converge to something. Let's call it x. So if it converges to x, then both sides are, everything's converging to x. So xn plus 1 converges to x, and this converges to x, but this is also converging to 1/4 of 2x plus 3, right? So in other words, these have to be equal. Okay, so you can just do that and then say, all right, if I multiply through by 4, right, and then subtract 2x over and then solve for x, you're going to get 3 halves, right? So you could figure that out that way if you didn't see what's going on with these numbers. So how do you want to proceed to prove that xn converges to the 3 halves then? Like, what does this problem remind you of? Okay, induction. I have to have a statement of induction. So there is going to be induction involved, probably, but what is the main approach we're using here, though?
Come from the definition of convergence?
Could use the definition of convergence. However, what else could we do?
Somebody's a Cauchy sequence.
Prove that it's a Cauchy sequence?
Can we show that it's like bounded and increasing?
Okay, so I would suggest proving it's a Cauchy sequence is going to be just as, basically you're going to have to use the definition because that's all we had really done. And that's going to be just as cumbersome as using the definition. So whenever we have these recursively defined sequences, we've seen a few other examples of it, our usual model for that is to use the monotone convergence theorem. Okay, so that's something I'm glad that you guys are here because you're going to put this in your mind. When you see one of these kinds of problems in the future, bingo, you want to think monotone convergence theorem. Now, because we wrote down the first few terms of the sequence, you might actually, another approach might be to say, I bet I can actually think what the formula for xn would be, which, the denominators here, this is just 2 squared, 2 cubed, 2 to the 4th, 2 to the 5th, so you might be okay to guess that that's going to be 2 to the n. Right? And then the numerator is like, it's basically, the numerator is like 3 halves of that, but then minus 1. Right? I mean, that's basically what it is. So you multiply with 3 halves and then subtract 1. So you could actually, if you wanted to, you could just claim this. Okay, because this I can then simplify. This is 3 halves minus 1 over 2 to the n. And now you can say, oh, as n gets large, this goes to 0. 3 halves minus 0 converges to 3 halves. So you could prove this by induction, that this is the correct formula. That would be one approach. Okay. I think I won't do it that way, because what if you didn't recognize that? I don't want you to be stuck, like, oh, I have to figure out what these numbers are doing. Right? So if you didn't recognize the pattern that was going on here, then you wouldn't be able to do this approach. But the approach of looking at these terms and saying these are increasing, so we suspect that we can maybe show that it's bounded and that it is monotone. Okay, so let's use the monotone convergence theorem. Okay, so I've got to show that it's increasing and that it's bounded. So let's start with increasing, or in other words, monotone. Okay, and we're going to do this by induction. We're going to do this by induction. Okay, so let's assume that x1 is less than, so the base case, actually we don't need to assume that at all. Just observe or note that the second term is bigger than the first term. So 1 is less than 5/4. Just obvious, right? Usually the base case is pretty easy. Okay, so we have that. Okay, so then for the step, for the induction step, what I suggest we do is assume that 2 consecutive terms obey the inequality, and then show that the next 2 consecutive terms obey that same inequality. So if we assume, let's assume that xk minus 1 is less than xk, and let's show that xk is less than xk plus 1. So we can just sort of set this up as 2 consecutive inequalities here. Okay? 2 consecutive inequalities. Okay. Well, let's start looking, if we look at this assumption here, so from the assumption, x sub k minus 1 is less than xk, but see what I can do is I can fill in the formula for xk in terms of the, or actually, let's see which way we want to do this. Actually, I'm going to change my mind here. Instead of from the assumption, what I'm going to do, this is what I actually want to show. So let me start with this xk plus 1 and try to show that it's greater than xk. Let's just go straight into that. xk plus 1, of course, is by the formula 1/4 of 2xk plus 3. So we can actually just put that in immediately. And now we can say, aha, xk, we want xk plus 1 to be greater than something. So let's make it greater than something by replacing 2xk plus 3 with, by the assumption, something smaller than it would be 2x sub k minus 1 plus 3. Right? So does everybody see what I'm doing? The assumption is that this number is bigger than this number. So of course 2 times this number plus 3 is bigger than 2 times this number plus 3. So this is bigger than this. Right? Now this though, of course, this is just the same, it's the right hand side with n being basically k minus 1 is starring in the role of n. So everywhere you see an n over there, now there's a k minus 1 here. So the formula then becomes x of k. It's just that simple. Does that make some sense? So in this case, I didn't actually, so here's the thing. You can start with the assumption and then work your way up to the conclusion from that. In this case, I actually chose to just take what I was showing, start with it, and then use the assumption in the steps in the middle. That turned out to be the easiest way. So this is an increasing sequence. Okay, great. Now, the other part of the monotone convergence theorem is bounded. Okay, bounded. So, bounded. And when it says bounded, you have to remember, you actually have to prove that it's bounded above and below. Above and below. Which one is easier here, above or below?
Below.
Right, and it would be bounded below by the first term, which is just erased. Okay, the first term was 1, right? Okay, so bounded below by x1 equals 1, and that's since xn is monotone increasing. Okay? So it's bounded below by 1. And then what do we suspect that it would be? So we're going to have to make a claim here. Xn we would claim is bounded above by what would you suspect?
3 halves.
Right, 3 halves, right? It's kind of converging at 3 halves from that direction. Okay? And how would you suggest we would prove that part? Induction, definitely. Definitely induction again. Okay, because you're proving this for all natural numbers n, right? Okay, so the proof here, what we would do, we look at the first term, x1, which was 1. Yep, that's less than or equal to 3 halves. Okay, so that works out really well. Okay, so then the step part here of the induction is going to be, so we're going to assume, I guess we can assume that x of n is less than or equal to 3 halves, and then we need to show that x of n plus 1 is less than or equal to 3 halves. Okay, right? Gosh, I really erased everything I need here. So I have the formula. I have the formula for xn plus 1. Let me just remind you, I've got it in the question. I just forgot to keep it on the board. There's the formula, right? Okay, there's the formula. And we want this to be less than or equal to 3 halves. What do you suppose I'm going to want to do?
74.
So what equal to 3 halves? Well, we're trying to show that this whole thing is less than or equal to 3 halves. And what do we know already?
xn is less than or equal to 3 halves.
So what can I do with that?
Substitute an n and then say that that's less than or equal to.
Right, if we just simply put in what xn is less than or equal to, it's going to look like that, yeah? So that's going to be 6 over 4, which is 3 over 2. And there you go, that does it. Okay, so therefore, xn converges by the monotone convergence theorem, and then you just have to do that argument I showed you earlier to prove that it's 3 halves is the limit. Okay. If you want to, of course, you can try on your own time to just prove the immediate formula for xn that I wrote on the board. That'd be good practice. That would also be done by induction. So a lot of these problems with the recursive definitions are naturally suited to induction because you're using previous terms of the sequence to get to the next terms. So induction should be a natural thing. These problems usually, I mean, I've taught this class a number of times, what people, when they see these problems where it's a recursive sequence, recursively defined sequence, usually that's a big clue. Oh, this is probably something I can do by induction. Right. So that's really the approach I think that you want to take with that. Okay?
And to show that it converges to 3/2, do you mean the method that you used earlier by the left hand converges, the
Yes.
right hand converges? Okay.
Right, so this one goes to x, this one goes to 1/4 of 2x plus 3, but they're the same sequence, so whatever that limit is has to be the same value. Exactly. Okay. Good on that part? Okay, great. How's my time coming along? I don't even know. 7:50. Okay. We'll probably have time to finish this up mostly anyway. Let's look at number 4. So I give you a function f of x which is equal to x if x is in Q, and it is 0 if x is not in Q. Okay? So let's do that. And so now this is getting into the chapter 4 stuff that we just started recently. Basically we want to show, so we just barely got started on this the other day, but I think we've done enough that we can prove that the limit of f of x as x approaches 0 is equal to 0. Okay. So yet again, I think we should start by recalling the definition. Okay. So just as a quick recall, just in case it's not on the tip of your mind right now, the limit as x approaches c of f of x equals L. This just means for all epsilon greater than 0, there exists a delta greater than 0, such that 0 less than absolute x minus c less than delta implies absolute f of x minus L is less than epsilon. So something along those lines right there. So this is just recalling the definition. So in this problem, of course, c is 0 and L is 0. Okay? C is 0 and L is 0. Okay, so for the proof then, this one is just a straightforward proof. It's actually a very straightforward proof. So we're going to need to start with an epsilon greater than 0. This is kind of our rubber stamp. Let epsilon. Hey, Leg. You can sit in my office if you want. There's no room. It's up to you.
Oh, it's okay, no.
Okay, we'll be done in a few minutes.
No, it's okay.
Okay. Okay, so epsilon greater than 0 we given. And then what we need to do is do the scratch, right? Just remember this from Wednesday? How does the scratch work? Well, we put absolute f of x minus L less than epsilon and try and solve it for delta. Because given the epsilon, we're trying to find the delta. Remember, the epsilon determines a horizontal strip around L, which in this case is 0. And then the delta determines the vertical strip around C. And as long as x is within that vertical strip, f of x is supposed to be within the horizontal strip. I won't redraw the whole picture again, but that's the basic idea. So we're looking at the absolute value of f of x. In this case, minus L is, there's no L there. So we're just going to put this less than epsilon, right? And our goal is to solve backwards for delta. Well, what I'm going to want to do here is just say that, well, of course, f of x has 2 parts to it. But if f of x is equal to 0, then of course that's already true. So what I can say is that in the first case, f of x is equal to the absolute value of x. So, I mean, that actually, okay, that's actually a if and only if, isn't it? So, there is the condition on that. Okay. And this is really, so this is really the absolute value of x minus 0 less than epsilon. So your c value of 0, which is right here, is less than whatever your delta is going to be. So based on this scratch work, what do you suppose you want to choose delta to be? Same as epsilon. Exactly. Delta is just going to equal epsilon. Okay, good. So let's try that then. Let's let delta equal epsilon. Okay. And then basically from there, you just have to check that delta works. So check that works. So the check is just this line right here. Okay. So what are you going to do? You're going to say, well, assume that 0 is less than absolute value of x is less than epsilon. And I'm just putting in c equals 0 on that. Okay. So I actually already know that this is true. Okay. So the absolute value of x is less than epsilon. Now, what? Yeah.
Is that supposed to be delta? And then we. Oh, just
No, I've actually.
Just, you're already subbing that in.
Correct.
Without writing. Okay.
That's correct. I'm just putting in the epsilon as the choice of delta to begin
Okay.
with. Now, we want to get from here to here, right? In order to do, we've already kind of got it right here, but I just want to emphasize that there's really sort of two cases here. If x is rational and if x is irrational. So if x is in Q, then, of course, the absolute value of f of x, right, I'm checking this condition, the absolute value of f of x is just equal to the absolute value of x, which we already have said is less than epsilon. So we get less than epsilon in that case. And then if x is not in Q, so slow me down if anything's not clear here. In this case, the absolute value of f of x is just equal to 0, which is also less than epsilon. Okay, so please don't draw your limit conclusion until after you've verified every x in the domain. So of course, this covers the whole domain, both of these cases. So now you can say, thus, the limit of f of x as x approaches 0 is just 0. So this is actually not that hard of a problem, but I decided to put it in here just because we've barely been getting our feet wet with the limits of functions stuff at this point. I just thought it might be helpful to look at that. Are we all right on that? Does that make sense? Okay. Question? If not, I'm going to do this last problem. The last problem is actually kind of a long one because, well, I'll explain in a second. I don't think I'll do the whole thing. I'll just do one case and then I'll leave you guys to practice the other. There's actually like 3 cases here. So I'm just going to do one of them. Basically number 5 just says to prove that the limit of x squared as x approaches c is equal to c squared. Okay, so it turns out that you kind of need to do it in 3 cases. One case where c is positive, one case where c is negative, and one case where c is actually equal to 0. So I'm going to do the case where c is greater than 0, and then pretty quick modifications will allow you to handle the other cases. Yeah.
I don't see why we need to split up in cases like that.
It may be possible to put them all into one. Well, we'll see when we do the proof. It may be possible to put them all into one case if we are careful with our absolute value inequalities, but it's just it's a little tricky. I think you may not see that yet, but it'll show up. We'll see. So basically, here's 0 and here's c on our x-axis or whatever, right? And we want to prove this. Okay. So, as usual, we need to let epsilon greater than 0 be given, right? And use the definition. Okay, and then of course we're going to do our scratch work here. On the scratch work, we're going to be looking at absolute f of x minus L less than epsilon. And of course, in this case, the L is just c squared and the f of x is just x squared. So I'm just going to put those values in right away. Excuse me. So absolute x squared minus c squared. Anything you would recommend that I do here?
X plus c, x minus c?
Yeah, this factors as x minus c times x plus c less than epsilon. Everybody okay with that? Now remember, what we're really trying to get to is, something where we're going to have this as our assumption, right? So we're going to find our delta from here. But in this case, okay, so I could actually solve for absolute x minus c right now. Okay, so if I did that, I could solve absolute x minus c is less than epsilon over absolute x plus c. Now, can I just make this my delta?
You can have C in there,
You-
right?
It's okay to have c in there. Yeah, the c is not the problem. The x is not a fixed number, right? X is this variable along the x-axis here. So this is actually not going to work. So we actually were doing an example of this right at the end of class on Wednesday where we were doing a quadratic function. Anytime you do a quadratic function, you're going to have this issue pretty much. So what you need to do is come up with a preliminary delta to sort of restrict, so that you're already going to restrict which x's you look at. Because if you allow yourselves to look at every single x, right, then x could go all the way to plus infinity or whatever and make this denominator huge, which would then make the whole fraction really, really small. It would be unwieldy to sort of get I mean, basically if x becomes infinity, you basically have 0 here. You have a constant number divided by infinity is like 0. Well, you can't choose delta to equal 0. So you need to kind of force the x's to not roam all the way up and down the x-axis. So what I'm going to, the way I control this is I'm going to choose a preliminary delta. Preliminary, if I could spell, delta. Now in the one that I did in class, I think it was x was approaching -5, and I just let delta equal 1 so that it was between -6 and -4 or something like that. I don't know if you guys remember the example. It's been a few days. But in this case, it's not quite as clear because you don't know how big or small c is, right? And so it might be... I mean, it would be good to just kind of keep the interval kind of pretty small around c. I don't necessarily need it to go, I don't really want it to go past 0 here. Okay? So what I'm going to do in this case is I'm going to choose it to be c over 2. Whatever c is, I'm just going to divide it by 2. So for example, Eric, if we were doing c less than 0 as a separate case, we would have to put absolute value bars on that because delta has to be positive. So you could do that, right? So the homework after this problem is going to be how do you handle the negative situation or the equal to 0 situation. This preliminary delta then basically is going to force us to have x between c over 2 and 3c over 2, right? So in other words, here's your new interval, c over 2 and 3c over 2, like that. Okay, so x can only be, so the biggest that x could be would be 3c over 2, which means the biggest that this denominator could be would be 3c over 2 plus c, 5c over 2, right, on the bottom. That's the biggest denominator, which would be, that would give us the smallest delta. Okay, so thus, I'm just going to put it this way, absolute x plus c is less than 5c over 2. So epsilon over x plus c, right, whatever that is, it's greater than, I'm going to basically flip that inequality over. So so there's an epsilon on top, and then 1 over this one would be greater than 1 over this one, which would be 2 over 5c. And again, Eric, you can see that if c is equal to 0, right, this is going to be a problem, so that's why it's another case, separate case for that. So if we choose our delta to be this, in other words, if we assume that x minus c is less than this, well then x minus c will definitely also be less than this, which is then going to allow us to start here and go through our scratch work backwards. See that? So we're actually, this is going to be the delta that we're going to take. Well, the minimum of this one with the original preliminary one. So in order, let me do that right here. So let's choose, let me write this down and then we'll look at it again. Choose delta to be the minimum of c over 2 and 2 epsilon over 5c. By doing that, you're going to restrict the x's to be in this range. And when